So, good morning. We can start now the last 2 days of the school that will be devoted to the Green's function approach. Okay? And we already seen that spectroscopy can already, at least electronic excitation spectroscopy, can already be tackled with already one particle approach, which we like. Of course, it's very fast, and we know reliable approximation of it, even if it's far from being great, even for those quantities who are observable of that theory. For example, in the Kohn-Sham approach, we know that the only thing that is exact in principle is the density, and nonetheless, we use it to calculate not only total energy, but also, for example, band structures. We know that we shouldn't, but since it is not that bad, we still do. And for example, as I said, we use it for, of course, total energy, but also for construction, and why not also to calculate some spectra. In particular, we have seen that some band structure are not at all badly described by DFT, even LDA, GGA. This is even simpler. This is K dot P, but it's equivalent in DFT, LDA, and these are only the valence bands of gallium arsenide. Here, the band gap would be completely wrong, but you see why it is very appealing to have a one particle picture when you can compare with experiment in a very good way. So you can explain the experiment. And we know that instead, if you look at something else, for example, the band gap, we systematically underestimate it. And we know that there is the fact that we use an approximation, but also the fact that we are interpreting something that should be interpreted as such. The homo-lumo gap in Kohn-Sham is not the photo-emission gap, even if it were exact. So we have to go beyond this. The same is for the spectra. We might imagine to have our one particle approach with function and eigenvalues, for example, in Kohn-Sham, and we can start by creating our first spectrum. We put it into the formula, and we get the imaginary part, scopic of this quantity here. Remember, by taking G equal G prime equal 0 including space, and we compare with the experiment. This is the case of the electron energy loss of graphite. Great. I mean, on top of the spectrum. And here I remind you again, here there is no rescaling in the theory. This is exactly the number that you probably might have obtained with the P on Tuesday, or you will, by doing this kind of calculation. And of course, it's enough to go to something else. For example, Valerio already shown this, the optical absorption of argon. You do it with the independent particle approach, and you obtain this that has nothing to do with experiment. And this is typically the case for optical absorption. So we have seen one way, which is the DFT. And today we're going to see another way with Green's function. Today will be devoted to the one particle Green's function. So in the first part, now here, we will introduce the concept of Green's function, and we'll have to define what is essentially the GW approximation. And in the second part, with Matteo, we'll see actually what are all the technicalities of doing a GW calculation, because it's far from being a black box. So you need to know some things. Great. So we have to go beyond one particle approach. And so typically one starts by this. And if I start from the definition of the Green's function, well, in 10 minutes, we will arrive in the definition of the GW. And for all those who already know all these things, it will be great, so we don't waste time. But now, for all those who are not already expert in that, let me take a step back and start a little bit before that, okay? So the Green's function is a very, very general method. we use it in many fields of mathematics, and of course we use it in physics for for the solution of some problems. And has nothing to do with the electronic structure calculation, nothing to do with quantum mechanics. It's even older than that, and is a generic tool to solve or to approach the solution of problems typically formulated this way. We have an operator, typically a differential operator, and we want the solution of this equation here, for example, when there is a certain external driving force, right? I show you one example, because it's particularly interesting for us. This, the Poisson equation. There is a differential operator acting on something that is our unknown, the potential, and there is an external contribution, which is, for example, density. So the solution here will be, what is the potential generated by a certain distribution of charges? Classical. Here, there is no quantum physics here. This is yesterday. It was shown in another form using the one of the Maxwell equations. The divergence of D is equal to 4 pi n. That's the Maxwell equation. If we take the potential, then the field as the gradient of the potential, we end up with the equation. Okay, so this is very general, and we would like a strategy. There are many, of course. Green function will be one. To want to have to calculate this potential. Okay, so the first thing that we do is the following. We define the Green's function as a solution of this equation, of an associated equation to this. We forget about the F, the driving force, could be anything. We forget about it, and we take this definition. The Green's function is the solution when of this equation when we put here a delta. So you already see we already put some non-locality. This depends on x and y, while differential operator act only on x, and we want this equality. And you already see, if you think in terms of matrices, if this were a matrix, this were a matrix, they would be the identity. So you can already see that the Green's function essentially is the inverse of the operator that you want to solve. Right? But symbolically, you could write that G is equal L to the power of -1, right? Okay, so now we do a little bit of algebra. We multiply both sides times the F, which is our function. We integrate over, and on the right side, of course, you have, again, F of x, if you integrate over, right? Here I exchange the integral with the differential operator. It has to be a linear operator. I forgot to tell you that. I'm talking about linear operator. So we can exchange those things. And so you hear that we integrate over. So here we have F, which by definition was just L applied on U. So we can recognize that this is U, right? So our solution is given by the Green's function applied on F. So if we have a way to solve this equation, the equation for the Green's function, and to, when we know it, for the generic problem associated only to L, then we can apply to any particular F. So the solution will always be G multiplied by F integrated over. So it will be applied to any possible equation of this side. You see here we haven't solved anything so far, right? We have to either solve this equation or we have to solve this equation. So the knowledge of G is still equal to the difficulty of the knowledge of U itself, right? There is no miracle here. But this method is indeed very appealing for many reasons. For example, it automatically includes the boundary condition inside. So there are several helpful points, and also the fact that it's universal. We solve this, and once we know with the G, we can apply it no matter what F we put here. Okay? Please stop me if you have doubts or points that you want to clarify. Okay? And in fact, we can apply it here. We would like to apply it, for example, here. If we know the Green's function of the Laplacian v equal beta, or equal 0, we could know, right? And in fact, okay, you can do it also for in time, not necessarily a differential operator in space, but it will be the same thing in time. This is another example. And here is the Wikipedia page for Green's function. At a certain moment, this is one snapshot of it, one part of it. It's not the full page, but there is a table of Green's function because it's so important that for many differential operators, you see that there is the equivalent Green's function associated to this operator. So you see there are many operators, linear, second order, differential in space and in time, linear in time, second order in space. You have all the combination. So you're really many. And in particular, if we go back here, we have the Laplacian operator, three-dimensional, and which is just 1 over r. Okay? So we can apply to the first example. Oops. Oh, I didn't put it. Sorry, I didn't put it. So what will be if you apply it to the Poisson equation? Do you have any suggestion? Of course, you know by already the answer about that, but what is if we use this differential operator for the Poisson equation? Any suggestion? What will be V of R if we apply this? Go ahead.
It will be this times the source term, so it's minus 1 by n.
And so we have to integrate these things. Here it's with respect to the origin, but this was already in R, so we cannot use the R, we have to use R minus R prime. So it would be, what is it, minus 1 over 4 pi R minus R prime. And then times the source. Remember, the source was minus 4 pi n R. So we obtain integral of n prime, right? R minus R prime. Here, right? Which is the
Coulomb.
Yeah, this is the Coulomb. What is this potential? This is the actual potential. Of course, the actual potential is the solution of the Poisson equation. So it's the exact solution of a classical distribution of charge. What would be the potential of a classical charges? It will be R3. R3 is exact in the limit class. Then you start considering electrons as quantum objects, and so you have to include the exchange and correlation, of course. But otherwise, this would be the solution, and it's not the only way to solve this, but it's one way to solve the Poisson equation using the Green's function. Okay? And now we go to the quantum problem, in which we also have an operator that acts on something, which is typically our solution. Actually, here is written slightly different, and so we like the previous things, so we write it like this. So that here again it's the operator acting on something, and here on the other side we have just the 0, which is even better, no problem. And so these are typically energies. So to make it really general, we just consider a generic quantity, Z. You'll see why this is important to consider it Z, even if typically the E are real quantities, but let's put it in a general way. So this is, again, an operator, differential operator, acting on something equals 0, and we want to find some. Okay? And so the Green's function is already obvious. It's the the opposite, sorry, the inverse. This is the formal definition of G. Of course, this is an operator, it's not a division of a number. This would be Z minus H to the power of -1, to be exact, but it's the formal definition of the Green's function associated to the Schrödinger problem. Okay? With the identity operator, you know this, right? The resolution of identity, you can always express the identity as a sum over all possible eigenstates. Base, if you have a base of your Hamiltonian, you insert all the possible states. So I0 is the ground state, first excited state, all the possible states. If you sum them all, ket and bra, you will obtain 1. And if I want it in the position representation, I put an R prime and R, and I have my Green's function in real space. This would be my Green's function in real space. Do you think we can do something else here? Because now we have the eigenstate of the Hamiltonian. What we can do?
We will have epsilon, the I at the denominator.
Epsilon, you mean E?
Yeah, sorry, E.
Yeah, exactly, because H can be applied directly now to the eigenstate of the Hamiltonian, and we'll have our Green's functions here written in the position representation. And well, the Green's function is written in terms of the eigenstate and eigenvalues of the original Hamiltonian that we want to solve, of the original operator. And not astonishingly, the eigenvalues appear in the denominator because it's the inverse of what it is. This G is the inverse of H in some way. And again, we haven't solved anything because in order to know the Green's function, we have to solve the many-body problem, not only the ground state all stands, because, and of course, maybe we don't need the Green's function if we are able to solve the Schrödinger equation for all these states, right? But formally, the G contains, and it has poles here, you see the poles, in all the energies of the system. The first one will be the ground state energy, first excited state, okay? And again, this is not even necessarily true for this quantum problem. Here I took my scan of my copy of the Jackson. So it's a classical electrodynamics. And in the first chapters about the problem in electrostatics, when he has to solve a generic equation like this, so it's again similar to a Poisson equation. If we go down, it works a little bit, it defines some functions that are orthogonal among each other, and at the end, you arrive with a definition of something that is called the Green's function, that expressed in terms of eigenfunction and eigenvalues of the original differential operator. So it's not quantum, it was known for a century now. That is one way to write your problem in terms of using this for your solution. Okay? Okay, so what? So we have this Green's function that is expressed. Sometimes this is called the Lehmann representation. Okay, we've already mentioned before the Lehmann representation of the Green's function in terms of eigenvalues and eigenvectors of the Hamiltonian, not of G, of H. Okay. Okay, so now if we consider this Z being not necessarily completely real, we have a little bit of an imaginary part. This will help us in doing the definition of the spectral function. So the spectral function is the imaginary part of G, and you'll see that it will be essentially related to the delta in those energies. So this is why we actually want to use the spectral function. We will see in a moment also applied to the electronic problem. But because as the G contains in the poles energies, this will be peaks in the spectral function. So if you are able to plot the spectral function, you will see peaks exactly at the energies that you want, okay? In this case, are the energies of your many-body problem. Great. However, we have to solve this problem here, and is exactly what we would like to avoid. And this is the machinery that we want to explain today. How to avoid going through all this psi 0, psi 1, psi 2, because we don't want to solve the many-body problem, Schrödinger equation. Okay, so the question is there another way that, for example, we can exploit the fact that G has pole in the energy that we want, but we would like to find G in another way, of course, not by knowing all the possible eigenstates. So, any ideas?
I mean, we have a function so it's single particle.
Single particle. Okay, let's go in single particle. In a single particle, this is always good because we know how to solve, in that case, the real problem, right? Because the Hamiltonian is factorizable, you have a multiplication of wave functions, and we have the eigenvalue. So this is a problem that we know how to solve. So what will be the Green's function in this case? Well, before going to that, let's imagine, so we have in this independent particle picture, right? So let's imagine to do that. We create a state, we consider a state that we call a trial state, okay? It's not specifically, of course, if this state is one of the eigenstate, well, the system will put a particle in that state, we will stay there forever because it's an eigenstate and it's useless to do any propagation. But let's suppose that we prepare a state. We don't know how it compares with respect to this. And we study its temporal evolution. This is quite obvious because H is time independent. So the evolution is simply the application of this operator. Okay? And now we insert again the resolution of the identity of all the possible eigenstate. And so we apply H0, we know how to apply it on Phi, right? We have just the eigenstate, the eigenvalues. And so in this case, we can define our Green's function as really the operator that propagates a trial state from time 0, let's say, to time t. For example, this is typically at the origin of the definition of a propagator for a Green's function. And here we're not talking necessarily about electron, we're talking about generic, this is even classical. It's a generic propagator, in this case in time, okay? And of course, we can decide to see in position representation what this states what is the probability that this state, for example, ends up in a state with a particle in position R. Well, we do the same thing, and we will have the Green's function also in the position representation. So we have inserted again here the 1, and so we have a certain state that we prepare. We calculate the probability to be an electron, for example, in position R1. We propagate with this operator, which is the Green's function, from from R prime to R. And we have our probability to find the particle at the time t, in position R. And this is defined by let's say, driven by our Green's function in R prime, and t. Actually, here you always consider t minus 0, but the position time is dummy. But there is always a time difference, okay? In fact, it's defined like that. So our Green's function is defined always like this with the theta, so the t is always bigger than 0 in this case. Okay, So we do a Fourier transform of this. We have it in time. We can do it in frequency. By doing this Fourier transform, we will have 1 over omega minus h0. And again, by inserting our identity here, we can apply h0 to psi n. We'll obtain epsilon n. And this is our Green's function. As we said, in the case of the, for example, conic sham, but this will be any independent particle approach. In the moment we have this, indeed the Green's function is just the sum over the eigenstates in the numerator and the eigenvalues in the denominator. Lemon representation of this H0 operator. And so we see that this epsilon n are the eigenvalues, sorry, the poles of the independent particle Green's function. And thanks to the Goupin's theorem, we know that these are also the energy of the electrons, right? This is something that will help us in a moment. So when you say there is a probability to find a particle in R prime, that means that you start from the vacuum level and you create a particle in position R prime with the creation operator, and then you do the same thing on the other side. It's a creation operator acting on the bra in R. And so please keep in mind these two equations, because these are exactly the starting point for our Green's function in the quantum realm for electrons. The fact that we would like something like that, so a Green's function written in terms of something in the numerator, and it has the poles in the energy that we would like to have in the denominator. And it is essentially defined by this kind of operator here, the creation and annihilation operator. Okay? So for the case of independent particle, this was the definition. Okay? And now we get back to our point before. You see, we write this with a little bit of element here, but maybe we can go step by step. So now we start from a system with interacting electrons. It's not anymore an independent particle system. We have a full system and electrons interacting. The Hamiltonian, we know, kinetic energy, the Laplacian, plus the interaction term, 1 over r minus r prime. Okay, so there are no unknowns in the Schrödinger equation, right? And the external potential due to the position. Okay, so let's suppose that now we put in the system an extra electron. So we use the creation operator, we put it in R prime at a certain time, T prime, which is completely dummy. Okay, but we say that this is very fast. We propagate, we will see how we propagate. So we go at a certain time T, and at position R, we destroy one particle. Okay? And we take the probability of this event by doing the expectation value of this series of events in the ground state. Of course, we have the theta always, and we define this as the Green's function. Here I put P because we are describing, we have said that we have created a particle, an electron, a position R prime in D. Okay? This is our definition, and again, is defined in terms of some many-body quantities. These are this creation operator and annihilation operator. We explicitly write the time evolution operator for these things, which again, since our H is time independent, is very easy. We don't have ambiguity here in defining the evolution of this operator. And again, here, you can do something, right? What we can do? Since there is H and there is psi 0, can we apply it?
We can consider n plus 1 until 1 minus 1.
Well, we'll arrive to that. But before that, we can, so there is an application, here H can be applied to this. And this H can be applied to this. Inside here, indeed, we will need to do something. But slow, exactly. So we apply H and we have E0, which is the ground state, because this is the ground state wave function, so we'll have the energy of the ground state. And immediately you see now that the whole things depend only on t minus t prime. It's obvious, because time is homogeneous, it doesn't matter when you start doing this. Okay, so formally you can Fourier transform it, and you have it here. So here you have to pay attention to something, because, so this is in the position representation, what is called the one particle Green's function for a particle, and it is really the resolvent of the H, which, so the Green's function here is a resolvent, is one resolvent of the many-body Schrödinger equation, okay? It's not the resolvent. In fact, we will see afterwards that we'll have an infinite resolvent of H. H is a many-body thing, right? So, but the fact that we say we are taking the specific matrix L in the ground state of one creation operator and one annihilation operator, this will be one of the possible resolvent of the Hamiltonian. We'll see that the two-particle function, the three-particle function are written in exactly the same way. We will have more things that will be still resolvent of the full Hamiltonian, okay? But the full Hamiltonian doesn't have one resolvent, which is the Green's function of one particle. It has it also for two particles, three particles, n particles, okay? But it's very appealing considering this like that. Now we can do the same thing for example, the creation of a hole. It will be the same thing. We create a hole in R and T, we propagate up to T prime, and we destroy this hole R prime, and so we will have the probability of the propagation of the hole, and we follow exactly the same path, and we're going to have a very similar result that we can typically put together using this time evolution operator. You see here there is a commutator, psi dagger minus psi dagger psi, and the time evolution operator always put the bigger time on the left, smaller time on the right. And so if you compare with before, this is what it does. You put t primes here on the right and t here, because there is this theta function. This was for the particle, and this is for the whole, t smaller than t prime. So it's not something very complicated, but it's it's in order to have both the propagation of the whole and on the left one in one definition, the Green's function. But be aware that it contains two pieces, one for the description of electron, one for the description of hole. Okay? There are many other possible ways to describe the Green's function in terms of retarded quantities, advanced quantities, in terms of greater and lesser that are related instead to the occupations. So there are many possible ways, but one is enough already to describe everything. Okay, so again, we will write it like this, as the sum of two pieces when we go to frequency space. And here we do the suggestion of Masoud. We said, maybe we can put something here in this one, in this one that appears here. We can use again the resolution of identity, and we have to specify what states we put here. And we don't have a lot of choice. Actually, we don't have a choice at all, because you see here, this destroy a particle. So when we apply this to the ground state of n particle, we will end up to some state of a system with n minus one particle. So since in the Fock space, state with the different number of particles are by definition orthogonal, we can only insert here states that have n minus one particle. So this is the resolution of identity. So these are all the possible ground state, excited state, all the possible states of a system with n minus one particle. And for the same reason, on the left side, we have to insert here all the possible state of a system with n plus one particle. If we want to use the resolution of identity here, because this is a state with n plus one particle, this is a state with n minus one particle. And when we do this, we can again say, well, H, I can apply it here now. And H, I can apply it here. And so I will have the energies, all possible energies, not only the ground state, but all the states, of a system with n minus one and n plus one particle. And so I put them there, and I end up with this new writing for the Green's function. Again, it's called the lemma representation, in which the poles of the Green's function are in the addition energy and in the removal energies of the system. You see here in the poles, there is the difference between the state with n minus one particle minus the ground state of the system with n particle. And the same here, the difference between the system with n plus one and n zero. And this, if you remember, was exactly the definition that we wanted to describe photoemission. In photoemission, we have with a photon, and we remove one electron. So we end up with a system, schematically, of course, with n minus one electron. So this was the operative definition of the energy of an electron, because you cannot have other than an operative definition for defining cyst. It has to be a measurable procedure. And the only way to say what is the energy of the electron in the system is to remove it. Is to say, I measure before, and the system has n electron, and I measure afterwards when the system has n minus one electron, because one I managed to kick it out. It can be from any state. And this difference, this total energy difference, is the definition of the energies of the electron when it was in the system. And this is exactly what appears here. You see here, there is a system with n plus one electron in any state. It's not necessarily in the ground state, right? Could be in the ground state if I put it in the lowest possible state, but I can even add an electron in a very high state. This will be an excited state of the system with n plus one, right? And I do this energy difference, this will create a pole in the Green's function. So the Green's function has poles in all possible addition energies. So if you think about it, it will be in all empty states of your system. And this has poles in any removal energies, all the possible occupied state of your system. Many body states. This is sometimes is made more compact by calling these nasty things here F, let's call it F, and by considering this energy difference as epsilon s, that are the energies of the electrons or the energies of the holes.
With this definition, can you also describe like absorption where the number of particles is the same with the Green's function?
Not yet, no, because in this moment, the only thing that we did was to add one particle and destroy it. For doing that, and we'll see in the next 2 minutes, we will have to create one particle and one hole, propagate, destroy. And in that case, we will have different denominators. Other point here, because this is essentially it in terms of what is a Green's function and what is related to. And of course, again, here we haven't solved anything so far because everything is defined in terms of the many-body states and many-body eigenvalues. That is the formal definition of the Green's function for a system of n interacting particles.
So, to answer your question, you will need other two particle operators, and so 4 operators, two psi and two psi, to have information about optical excitations. And this, with 4 operators, you will see that it is the particle Green function that later you will introduce. This is one particle Green function does not give you the propagation of an electron hole, and so the excitation, the electron hole excitations, like in optics.
So far, we can only remove or add one electron. An extra electron. It's still an indistinguishable particle from all the other electrons. In fact, I never said that here we create a particle and then we later destroy it, the same particle. We destroyed a particle. They are indistinguishable. Okay, that's what makes it complicated. Okay, and so you will always find it in an even more compact form with just one thing, in which the ES are either this or this, depending then on the sign of the this quantity. So depending if the energies of the system is bigger or smaller of the Fermi energy, the chemical potential. If you are up, that means that you are adding an electron. If you are down, that means that you are removing an electron. So sometimes you find it in very compact. But remember, this essentially relates to these two very clear object.
This eta that we have is a small value of imaginary part. I know that we usually have it to have when we have here Fourier transformation. Is there any other physical meaning behind that?
Yeah. So as you said, in this definition, it comes, and I've been sloppy here. Here there should be limit of eta going to 0 plus, to be more precise. So this is a mathematical trick, because to do this Fourier transform, we write this theta function here has the limit of eta going to 0 of integral over e to the power of I omega t divided by omega plus I. This is a definition of the theta in Fourier transform in omega frequency. And so while we put this trick for the theta, this permits to do this this Fourier transform very easily. Essentially, is this step that we want to do the Fourier transform. Here it's not clear. It's before it was clear. So here you see we have to do the Fourier transform with respect to tau p minus t prime of a function d theta of tau. So the Fourier transform of this, if you didn't have this, would be very hard and numerically unstable, and anyway we wouldn't know easily how to do. But with the theta, it's pretty obvious. You write this in frequency space, you multiply, then you do the Fourier transform of all, so you will have two frequency, omega prime and omega, but you figure it out, you obtain a delta of omega equals omega prime plus something, and you will end up with this form very, very easy. But there is still this definition which contains the limit of eta going to 0. So this is only maths. There is no physical meaning related to that.
Otherwise, the Fourier transform does not exist.
Yeah.
So this is a way to have mathematical trick to have the Fourier transform.
So you see, always this Fourier transform contains this exponential, no?
Yeah.
And this exponential, in order to have a meaning, you always have to specify the domain, where this exists. And so it happens that you cannot do it if you don't say, for example, if this t is slightly smaller than 0, slightly bigger than 0, and this is typically done with this eta factor. That without it, you will not be able. So now that we have done this, you can give some a posteriori meaning, but this will do it because afterwards we will introduce the quasi-particle approximation, and in that case, well, this eta is related to something very important, and so you can relate it to the lifetime of the excitation in play here. Here you remove, you create a hole that will essentially live only proportional to inverse eta. This will be more or less the physical meaning. But here we haven't done any approximation so far, okay? This is really Wigner's function. And when we take the imaginary part, we end up with something that has poles to our electron removal and addition energies, which is what we want, for example, in photoemission, right? And in fact, in photoemission, if you do that, we will expect, let's say, we will expect something like this. We have this delta peak where there are the removal energies and additional energy. Here I used different color because we have this this delta here, delta this. Delta this will have peaks with a certain intensity where omega is equal to this possibility to remove or add electrons. So we will have something like this, right? Or not?
Yeah, because of independent.
Okay, these are delta, right? For the moment. So there are peaks. These are the S of n plus 1 minus 0, so additional n electron. From the other side, there is the removal electron, and we put here, if it is possible, the chemical potential. So, for example, in finite system, we will define this as HOMO, which is the highest occupied state, and this is the LUMO, the lowest unoccupied state. Okay? But then this is not exactly how, if you really were able to solve the many-body problem and you will have all the states, you will zoom in a little bit and you will find, for example, if you zoom in here, you will find something that is a little bit more complicated. You will have really a lot of peaks, not just, I mean, you have a lot of peaks close by. And you typically have something like this. And the reason is because when you excite, for example, in photoemission, you don't put the system in one specific eigenstate of the problem. You remove many electrons. You do the calculation. Sorry, calculation. The measurement. Simo is not here. And you obtain essentially a current that then you associate to the many events that happened. So essentially, when you look at, you will see something more similar to this. And the reason is because you have many S. You have infinite S, all the possible excited state when you remove even one electron when you add one. So you will typically have something like this, that if you convolute a little bit, you will obtain more or less this picture. Okay? And let's do a summary here. This is, for example, what we obtain in for the emission spectrum of bulk silicon. Okay? So here you see that it's very similar to what I showed before. We have to look at this part. It's for the emission, so you only can remove electrons. Okay? It's not inverse solution, but this part we will not see. We go and see what they have done at Sottile synchrotron, tempo beamline. This is the spectrum, the spectrum, the photoemission spectrum of silicon. And now you compare it with your, for example, with your band structure. You put the band structure of silicon. This is again taken from Wikipedia. And you see that if you align the energies, more or less, you will see that you have the bands here. These are the bands. And then you have still something else. You see? And in your bands, don't have any. Don't have any. These are your SP bands of silicon. And the next band going down, there will be the 2S and 2P, which are, if it is 20, 30, it will be a 100. They will be here, the other bands. But in the photon emission spectrum, you see things, you see something. Okay? And in fact, the reason is because you have all this, extra states that you get because we are, sorry, I went in the wrong direction. Okay. You have this strange situation that if we were able to solve the many-body problem, you will obtain all these data. These are typically called quasi-particle when there is an obvious main peak in your picture, and there are other little peaks. These are called typically satellite. This is the nomenclature that we use that are associated with this spectroscopy. And so, to summarize, you have the one particle picture, the one that we did at the beginning, in which you have energies, finite and discrete values of this energy that are related to some potential in your Hamiltonian. You have also one particle wave function. So the spectral function contains only deltas, and you will have this kind of things. Then you have the many-body picture, in which again you have a lot of delta peaks, and lots of them, and you don't have one particle peak function, you have the wave function of everything. And well, no problem for the potential here. And then you have an intermediate picture that we would like to keep, which is this quasi-particle picture. So ideally, we would like something that in once we give you for one excitation the entire green curve in once. So in which the spectral function will not just be a delta, it will be something more as a function of frequency, in which we can already imagine that the potential entering must be frequency dependent. Otherwise, you will not obtain the solution which is frequency dependent. So this is what we are after. This is what we want to start from, and we want to completely remove the many-body picture. We don't want to solve the Green's function, sorry, the Schrödinger equation. Okay? And so we start again from the definition. We have all this, we have all these poles. Actually, the Green's function is used for many other things we don't discuss here, but the Green's function contains the density, its diagonal, the density matrix, can be used to obtain any observable of one body operator, can be used to obtain the total energies. We won't use here this for other observables. We want just this spectral function, okay? But this is possible. Okay, so we want to obtain that. And again, we start from an independent particle system, which we know what will be. No problem for that. We have seen that. And we want to go beyond. And the only possibility to go beyond that is to verify if we can do something. And there are not many things that we can do. Yeah. Okay, so we have this definition, and it's defined in terms of this many-body state. So we want to verify if there is another definition for G. Okay? So what is typically done is say, okay, let's write the equation of motion. We derive G with respect to time and see what happens. And actually what happens is not great, because here you see the only part that depends on time is this evolution operator here that appears here, and and simply this time evolution operator, which intrinsically is also dependent on time, but we can do this, these things. And so if we do it, there is one good point and many bad points. So the one good point is that if you start doing the derivative, I don't put here all the details, it's a bit tedious. I have the lecture notes if you want, okay? But what is good is that when we do this, we can define the G in terms of G0, whereas G0 is the Green's function of a one particle approach. That means that is the Green's function of the system without interaction. So it's just a Laplacian term and the external operator, no interaction. So we would know again how to calculate. And then we go over and we obtain this nasty things, which contains again G0, the Coulomb term, now, and this other object here, that you see the suffix 2, that is a two particles Green's function. So at the end, you end up, since you do this time derivative of the time evolution operator, what you end up, if you remember when you do the derivative of an operator, you write it as operators commuting with h. And when you start doing that, you will obtain something that is two operators. And so doing the derivative, the time derivative of the two operators that are contained here, you will obtain four operators, and they are here. I spare you the details, but this is what you obtain. You obtain a quantity that can be defined as the two particle Green's function. See here, in this case, we create two particles and we destroy two particles. We can do a parenthesis here about the two particles Green's function because it will be useful also for tomorrow's lecture. So she doesn't have to cover everything, but it's also partially answer to your point. Here you see, I define one specific two particle Green's function. Here I call the particle. So what I do is I create at time t prime one particle in L4, and at the same time a particle in R. This is my choice, okay? I could have taken in t prime and in t double prime. I can create two particles one after the other. But in this case, I choose a specific Green's function that creates two particles in two different points of space at the same time. I propagate them, and both of them, and I destroy two particles at the same time t greater than, right? In position R1, and again, I get the probability of this event. But this is the probability of having two particles added in these 2 points, and with the probability of removing them in these 2 points. And again, you can do all the machinery, you express the time evolution operator, you apply h to psi 0, and then you do the Fourier transform. And here you see you obtain another resolvent of the same many-body operator, but now you have two operators. And in this case, you really create 2 electrons, remove 2 electrons. And so, for example, this will be the particle. If you create and destroy, and then destroy and create, you will have the particle hole. And here you see this destroys a particle, this creates a particle. So once applied these 2 operators, you will end up with a state with n particles, still n. So if you want to now do this resolution of identity here, you would put all possible state of a system with n particles. So then you apply h, and here you will obtain Es exact state minus E0. And so here we will obtain the chi that Valerio expressed yesterday, which is the density response function. You will obtain the poles of this 2 particle function will be in the difference between a system in an exact state with the system in the ground state. No difference in particles. So it's the neutral excitation of your system. But only if you consider this particular two-particle Green function, which is the particle. This is the particle, you could define the whole world. Okay? So you have this two-particle Green function that, of course, doesn't help because now we have two unknown. And now you do another trick that I will not explain in details at all, which is this. The two-particle Green function, I express it as the product of two Green functions, which would be most of the things. I consider that the propagation of two particles, first of all, is the propagation of one particle and the propagation of the other particle, but this is not the full story, plus something else. And this plus something else can be demonstrated is just the linear response variation of the Green function with respect to an external potential. Vanishing external potential. So it doesn't matter what we put here, okay? We just put something and then we put it to 0 at the end of the job. But it creates this 1, 2, 3, 4 quantity here. So the G2 is 4 point because describe the propagation of two particles. So if we remove this, of course, we will have just the independent propagation of two particles. So we can put this back to the previous formula. And if we do that, we obtain an equation, sorry for all the indices, but it can get worse, in which the Green function is expressed with only one particle Green function, even if it contains this 4 point, which is 4 point, okay? But the ingredients, let's say, are the Green function, the Coulomb interaction, and the G of the independent particle, or sorry, of the non-interacting system. Okay, and this is a very difficult equation to solve, okay? So we don't typically solve, even if most recently we have done some effort doing ansatz for this. You can imagine this is the first order in G, differential in G, so you can do ansatz like, I imagine that G is in the form of an exponential and try to get something out of it, but it's very complicated. So what typically the people do is, well, look at this. G is equal to G0 plus G0 something G. Right? Does it tell you something, this kind of form?
Doesn't.
That's an equation, exactly. So let's imagine for a moment that we don't have this horrible term here, which contains this 4 cell. Well, we just put it to 0. We will have a Dyson equation for G with all known ingredients. And actually, here, what is G of two same indices? The density. So I have the density times the Coulomb integrated over, what is it? The density times the Coulomb, the Hartree. So if I remove this, all of this, I will obtain the Hartree Green function. So I start from an independent particle one. I add the Coulomb in this, I add the Hartree potential here. I do the Dyson equation of G, and I will end up with the G that is equivalent to do a Hartree calculation. So the lemma representation of the G's of this G, if I write in terms of eigenvectors and eigenvalues, what would be the Hartree wave function and the Hartree eigenvalues? So this is one approximation. Of course, very rough approximation. We are talking for an hour to obtain the Hartree function. Okay, but it's one approximation. And if we want to go beyond the Hartree, we have to consider this step. Yeah. Now here we do a little trick. We express, instead of delta G over dx, we write this in terms of delta of inverse G. This can be done. It creates two G's here. And I do that because otherwise I will not have a Dyson equation. You see, here, I don't have the G appearing explicitly, so I don't have the Dyson equation. G is equal to G0 plus G0 something G. And I don't have it here. But I can make it over by doing, instead of this, express it in terms of dg to the power 1, it will make 2G appears here. We can do this. It's very easy. And now I have a Dyson equation. Okay? I have G is equal to G0 plus G0 something, the something is BR3 plus all these, G. Dyson equation. And again, difficult, there is always this dumb term at 4 point. And again, let's forget about it for a moment. I cannot put it to 0. Okay, because otherwise it will put everything. Well, I put it to 1. I imagine that this is a delta in 5, 4, and 6, 4. So I put it to 1. What will happen? Atrifork. Because again, here I have the G times 3, 4, and you see they are the same indices, but the Coulomb potential is instantaneous in time. So this G is multiplied by a delta in time. So this is only a density matrix. So density matrix times Vc, it will be the Fock term. So this is the Hartree-Fock Green's function. And when we consider everything in that term, so this is not one, BC, G, and everything, well, we give it a name. We give it the name of self-energy. It has, after all, the dimension of a potential. In fact, it is a sum to the part of when there is big Hartree. So we call it self-energy. And this is the correct equation. And again, when we put this to 1, we will obtain a Fock. If we put all this to 0, we will obtain Hartree. There are two possible approximation for the full green Dyson equation for the Green's function in terms of the self-energy. So this is our G. Sometimes it's easy to consider our starting point G Hartree. In that case, we will have a new Dyson equation. But I mean, this is just moving the potential from one way to another. And here you see, I don't know anything about sigma so far, but already I can do this. I can take the imaginary part of the Green's function. So if this is not here, we know that this is the G0 Hartree. So it's the one particle approach. My lemma representation will give me just delta peak. Okay? And now if I put the sigma that has a lot of indices, so it depends on space and times, it's sigma 1, 2, so that means sigma R1, R2, T1 minus T2, so frequency. If I put the spectral function, something from this, I will obtain this value for the imaginary part of the Green's function. So I will have here in the denominator the real and imaginary part sigma, and in the numerator I will have the imaginary part of sigma. And if you try to figure out what this shape could be, well, it is exactly this kind of shape. And in fact, I can also put one shape. So I have here one shape for the imaginary part of sigma, and you see that if the imaginary part of sigma is a Lorentzian in a certain point, the real part by Kramers-Kronig will be related to this thing. So we'll do something like this, like we've seen for the real and imaginary part of epsilon, the same thing. And so this green will be this part. And you see that when the green part is 0 and the imaginary part is small, this denominator will become very, very small. So you will have a peak. And this is where it happens. And this gives the quasi-particle. But also, when this thing is not too big and the imaginary part of sigma is big, which is in this region, I will have a peak in the spectral function. And this is the satellite. So already by considering the possibility to have a frequency-dependent sigma, your imaginary part of G, so your spectral function, will have a quasi-particle peak and a satellite. And this is what we are after. We just have to find now an approximation for sigma, which is frequency-dependent. if we put again for sigma only sigma x static, we will obtain just the peak in a different position, but we will not obtain this this shape. And also in the case of artifact, we will not have the like that, so will be again just a delta. Okay.
Sorry. Okay, considering the fact that this image of sigma is related to time life, and this point you said that once this the imaginary part is large, we see satellite effects. Is it true to say that satellite effects have larger lifetime than the quasi-particle peak?
Well, generically, it is the case. Now I will have to verify if this mathematically holds correctly, because so in the quasi-particle picture, the only part that depends on the lifetime is this part. So it's this. You don't evaluate here, because this has nothing to do with the inverse, actually, imaginary part of sigma. Imaginary part of sigma tells you this width. So now, in reality, this typically is related to possibility of extracting an energy at that energy, extracting an electron at that energy. So that means that it will be related to what is the lifetime of this hole. So if I extract an electron, how much the system will take, how much time the system will take to fill it up. This would be a real the lifetime of this excitation related to this part. And of course, here, well, it depends on the physics origin of the satellites. For example, if this satellite is a plasma, because when you remove an electron, you can imagine that all the other electrons will start, oh, there is a hole, let's screen it. So they will move to screen that in a collective excitation, and this would be, for example, a plasma. So we know that the plasma has a different lifetime than the excitation. So the oscillation related to this plasma will be different, so will be a different energy, but also the lifetime of this, so how much this oscillation will endure is completely different from the lifetime of the particle. So physically, we will not have the same lifetime of the two kinds of excitation. But in this formula, if you look at this formula, the lifetime of this related to the imaginary part of sigma, only related to this quantity here. There is nothing here that tells us the peak. We just now we are imagining. But for example, these satellites, for example, in nickel, are related to completely different mechanisms. They're not plasma. They are typically hole interaction, electron-hole interactions. So there are three particles quantities that have even different lifetime. And so in that case, I wouldn't know, for example, if it is bigger or smaller than the lifetime related to the removal of electrons. I wouldn't know. I will have to check, because I don't really remember. So then we will have really to see what is the origin of this satellite. Okay? But in order to have it for sure, we need the sigma, which is frequency dependent. Otherwise, we will have a delta peak. And so, even if there is a nice mathematical derivation, here I will say, okay, I have my sigma, which is a potential. It acts like a potential, even if it is depending on two space coordinates. The sigma 1, 2 has R1, R2, and time 1, time 2. In frequency space would be R prime, and omega. So I consider an equation in which this sigma can appear, and I call it quasi-particle equation. Actually, there is a mathematical reason why to do that, but here you can imagine that by comparison with R3 and R4, you can imagine an equation that is really looks simply like that, in which you have a new potential beyond the R. And in fact, if you consider here only the GV and not the rest of this delta G minus 1 over delta Bx, if you consider T1, you will have here Hartree-Fock again, because this will withstand, this frequency dependent will disappear, and this will be non-local in space, will be the Fock okay. But we have this quasi-particle equation that is essentially where we want to act. But we need an approximation for sigma. Okay? As I said, you can have Hartree-Fock, which is again an approximation of the quasi-particle equation. Okay, so here we have one equation, two unknowns, G and sigma. This is our sigma. By the way, have you ever thought this equation? You see, GV, have you ever heard of gamma? So this will be GV, let's call it gamma, okay? Actually, if you put this gamma to 1, you have, again, Hartree-Fock. Now we do a little bit of something, because when we do this approximation, we put this to 1, we obtain Hartree-Fock, and we know that Hartree-Fock is not that great. I mean, if you are calculating total energies of atoms, it's very good, but overall, Hartree-Fock is not that great, especially for solids, right? We want something better. So we change this variation going through the total potential in such a way that now we have the variation of G minus 1 is very dot, and G total is very inverse. And this is the definition of the inverse electric function. This epsilon minus 1. And you remember, epsilon minus 1 times V is the screened Coulomb interaction. Okay? So instead of GV gamma, we will have a GW gamma, where this is our screened interaction. And here, when we put gamma to 1, we will see also another definition, but we will have GW for sigma, which is our approximation. And by doing this is a very good way, because you see here we make an approximation at this level, and we have Hartree-Fock. Hartree-Fock is not good, because essentially what it leaves out when you do this approximation, it leaves out the bare Coulomb, too strong. When we do the same approximation here, I put in this derivative to 1, we have GW, which is a much better approximation, because W is screened, is less strong than V, and you will see some result, but you know already that GW is better than Hartree-Fock or Hartree or independent or LDA. And another way to see this, beside putting again this to 1 because it's 3 point, it's better to avoid it. We can also see it in a different way by calculating even more formula. And again, I will not bother you with the details. But starting from these two, you can go on and define other values. You can see what is gamma after all, by the derivative, in which sigma appears again. This is nice. Now we have 3 equations, 3 unknown. Well, sorry, 4 unknown. There is also gamma. We don't know that. And W is epsilon minus 1V, or we can make it in terms of another quantity. This is P, and P is itself related to G. So I don't expect you to follow all this, simply that it is possible to define more quantities that are related to each other in such a way that at the end you end up with 5 equations with 5 unknowns, which are the Hedin's equation. And Hedin is this guy. That I was lucky enough managed to know him. You also did, right? Yeah, very nice guy. He died when we were in a conference. No, you remember we were in a conference with these pupils also. Okay, so here we have this 5 equation with 5 unknown, and the typical way to see this possibility. Well, we don't know where to start. We start with G, because in G we know at least one approximation for G, for example, G0. And we start, for example, G Hartree or G0, G Hartree-Fock, G Konesham LDA, we start with one particle. And then with G, you put gamma to 1, because you don't have sigma. So you don't have the gamma is 1. Then P will be G gamma, but gamma is 1, so it will be just GG. Sometimes we call this RPA, equation of two-Green's function. Then from the P we end up to W, which is W RPA. And with G and W we do sigma, still gamma is 1, and we have our approximation, which is typically called G0W0 or GW one shot. There are many names in these things, but this is essentially what it happens. And of course, you could continue and you can calculate again the new G with this the sigma. And so you will have now the eigenvalues in different positions. If you take the imaginary part, you will have a quasi-particle picture with a quasi-particle and satellite. Not necessarily good enough in this approximation, but you will have it. And so you can see it as a dynamically screened R3 because R3 is GP, and now we have epsilon in the middle, so you screened the Coulomb interaction, so it's a screened R3 dynamical because epsilon minus 1 depends on the fields. You can also have static. You will have statically screened R3, sometimes it's called cosec. Well, you have several. And you can put it in your quasi-particle approximation for GW. This is not that easy to solve. You will see it with Matteo that you have some caveats because it's not an eigenvalues problem. You see, because the energy that you want to obtain as an eigenvalue enter also here, so it's not an eigenvalue problem, but there are ways to solve it, typically in perturbation. Okay, so these were the results that I showed you before. GFT LDA. I put R3 because I stolen from Valerio's slide. That are too big because the V is too strong, the V on screen is too strong. And if I do GW, you are already seeing this, you obtain better value. Because after all, the GW is a much better approximation than considering an independent part of the picture. Actually, this is the GW one shot, this GW not. There are other things that are done in this article, like the quasi-particle self-consistent GW, that are extra way. It's not perfect, and you find also things that are even worse than these things. Here it will be perfect if you were on top of this dotted gray line, which is the experimental band gap with respect to the calculated one, but you are not on top, then you are even in worse case. And if you go to the spectral function, it's not great at all. Here for silicon, it gives you a satellite. So you see, you obtain a satellite. You obtain even two satellites, sort of, but it's not satisfactory. And for this, you have to go really beyond simple GW. And there are ways actually to do it. I'll show you one case, which is done with the cumulant approach. Indeed, by solving the original equation with G, no sigma was the differential equation with some ansatz, you can obtain this. But the point was that you can obtain now better one particle electron and emission energies. And so you can compare with photon emission spectroscopy with the GW. And in order for you to do it, you will have now to verify all the technical details because it's not, as I said, a one box, a black box calculation. There are a lot of little details to solve the quasi-particle equation. And you will see this after the coffee break. And here I put some literature, either the original headings paper where there is essentially everything that I said is there already in this old paper, but in this book is done with all the derivation and with the much, let's say, more modern way of writing things. And well, questions then.